So let's complete our discussion on modes in optical fibers. So we're looking at a graded index fiber with square law profile last time, and we discussed the TEM modes, right? Solving in the Cartesian coordinates. So today let's see if we solve it in the cylindrical coordinates. We get these LP modes. Right, so again, basically, we're looking at a refractive index profile which just depends on the radial coordinate, right? So a circularly symmetric profile. Okay. So for the specific square law case, it will look something like this, right? Where? So for something like this, which depends only on the radial coordinate, right? Or more specifically, for something which you can write as a function of r plus a function of phi. I mean, we don't have any function of phi here, but if the profile you could write it like that, like for example, in the last class we wrote it as a function of x plus a function of y, right? Then basically you can sort of use separation of variables and solve it, solve the wave equation. Right, so we'll solve it in the cylindrical coordinates today. So r and phi, right? And again the propagation phase. So again, basically, we plug this into the wave equation, right? And a similar time derivative is I omega, the z derivative will be I beta, and then we'll be left with the transverse derivative part. So just like in the modes for the step index fiber, right? So we'll have an equation in the transverse coordinates r and phi, which we can solve by using this separation variables. Okay, and then so if you plug, I mean, I won't write all of the steps again. It's the same as what we had in the step index fiber, right? And then we separate out the equations for r and phi, and for the solution for phi, we get like cosine L phi or sine L phi, where L is an integer, right? So this part of the equation remains the same, right? Because the refractive index just depends on the radial coordinate. So this part of the equation remains the same, solution is the same, and then we are left with the radial part. Okay, so the radial part looks like that. So same as step index fiber, except this was a constant in the step index fiber, right? N1 or N2, depending on overall cladding. But here this is a function of r. That's the only difference. So there is a question. So we'll see. We'll see the relation between TEM and LP modes. Right, so again, basically, you have to go ahead and solve this differential equation for this square law profile. Okay, and actually you can do it in a similar way. For example, like we solved for the quadratic profile in Cartesian coordinates, right? Like for the slab or for the fiber we saw yesterday, right? What you can do is you can replace R as some polynomial times some kind of Gaussian kind of function, okay, and then plug it in and then try to find relations between the coefficients of the polynomial, right? Like how we derived the Hermite polynomial solutions, you can do it in a similar way, okay? And what you end up with are what are known as Laguerre polynomials, okay? So it's the same thing, just the relation between the coefficients of the polynomials are slightly different. Okay, so the solutions look like this. So again, there's a Gaussian part here, right? And then you have a Laguerre polynomial here. Okay, so this is so the Laguerre polynomial has two indices. Okay, so for the LM mode, the Laguerre polynomial has index L and M minus 1. Okay, so M here of course goes again from 1 to 3. Right, so for each L, you can get a number of solutions depending on the value of M here. Okay, so what is this gamma here? Gamma is sort of the same what we had last time in the last class. So sort of this square root of V number divided by the core radius. Okay, and this NLM is a normalization constant. Right, basically this normalization constant ensures that again that this integral is 1. Okay, so and then how are these Laguerre polynomials defined? So if you look at Laguerre polynomial with index k and n. Okay, so you can see that so this Laguerre polynomial with index n is a polynomial of degree n, right? So this summation runs from 0 to n, where x to the p, right? Just like the Hermite polynomial of index m was a polynomial of degree m. Similarly, here just the form is different, so the coefficients here are different. So we can look at some examples. So for example, if n is 0, then this is just a constant. If n is 1, you can see it's just a first order linear function. Similarly, right, so now if we go to 2, it's a quadratic. right, and so on. Right, or you can use this generating function, right? So similarly, like for again, for Hermite polynomials, we had a generating function, right? So where we could take the mth derivative of some function. Similarly here, okay. So you take the m minus 1th derivative of this function, you'll get the level. Okay, and again we have constraints on like the values here. So again, like how we solve it is we do a change of variables similar to what we do in the Cartesian coordinates, and then we get some constant which we say has to be an integer for the polynomial to stop, right? So similar here, and from that we get a condition for the propagation constant beta, right? So in the Cartesian coordinates, remember beta dependent on m and n. Similarly here, we'll get a relation for the beta depending on L and M, right? Okay, so we get this relation for the propagation constant for a mode with index L. Okay, so in the Cartesian case, here we had something like m plus n. Here we have now 2m plus L. Again, the same argument holds, right? So for example, so this quantity is small. So you can do a Taylor expansion here, and then you will see that so beta first term is proportional to omega, but second term is just a constant which depends on m and L. So the group velocity again will be independent of the L and M indices, right? So no intermodal dispersion to first order. Same thing. So here you can see. So just like in the Cartesian coordinate case. Right? So of course both solutions are equally valid. Right? We could solve in Cartesian coordinates and get this TEM modes, or we could solve in cylindrical coordinates and get these LP modes. Right? So both are equivalent. So of course then there has to be some relation between the two because both are equally valid modes, right? So if you have such a case, right, like you have two sets of solutions, then for both of them to be valid, basically the only way is if you could express one of them as some linear combination of the other, right? Or take any solution from any one set and you should be able to express it as a linear combination of some degenerate solutions from the other set. Right? So that will be the case here too. So let's start with some mode profiles for these LPLM modes, right? Yeah, so the mode profiles will look very similar to the LP modes for a step index fiber, except that the exact radial dependence, the function is different, right? So there we had Bessel functions, here we have Laguerre-Gaussian functions. So these are also sometimes called so LG, Laguerre-Gaussian. Modes. Okay, so Especially nowadays, like for example, in free space, there's a lot of interest in these beams carrying orbital angular momentum, right? And those are basically solutions which have this exact form in free space. So they are known as the Gaussian beams. Anyway, but in a gradient index fiber, automatically the mode solutions are this. So the mode profiles look very similar to a step index fiber. Right? Only if you plot the exact functions, there will be slight difference, but sort of qualitatively they look the same. Okay, so the lowest order will be, so L starts from 0, M starts from 1, right? So the lowest order mode again is LP01. Right, so again if you use that expression for the mode, so again for L0, and M1 we have basically just a constant function in the radial coordinate, so there is no only the Gaussian function remains. The polynomial part is just 1, and then also the azimuthal dependence sine alpha and cosine alpha, that's also a constant because L is 0. Okay, so that's the only part of the mode which remains. Right, so you can see explicitly here it's a Gaussian mode profile. Right, and recall that actually this is exactly the same we got for the lowest order TEM mode, TEM00. Okay, so basically the lowest order LP mode is the same as the lowest order TEM mode, right? So again, we could have two degenerate modes with two orthogonal polarizations here, so Y polarized or X polarized. But the mode profile is just a Gaussian, right, in both X and Y coordinates, or any radial coordinate. Okay, so here the relation between the TEM and LP mode is obvious to see. Now let's look at some higher order modes. So LP11. Right, so we go to L equal to 1 and M is also 1. So you can see from here now we have a linear function, so there will be an R term here. And then we'll have also an azimuthal dependence, L is 1. Right, so again we'll have four-fold degeneracy for these type of LP modes where L is not equal to 0, because now we have two-fold degeneracy from here and then 2 from polarization. Right, so how do these modes look like? So again, you have an R here. So the origin, the field is 0, right? And then you have a cosine phi or sine phi profile, which gives you an azimuthal dependence. So if you take, for example, the cosine phi, you will get two loops like this, right? So phi equal to 90 degree, there will be a null. Right? So there it could be, so this would be the y polarized cosine phi, this will be the x polarized sine phi, sorry, cosine phi. Right, and then here. Okay. So for the sine phi solutions, there was 0 along phi equals 0. Okay, so again recall the TEM modes. So these look like, so you can see that this looks like, so now you have a 0 along the x equal to 0 line, right? So this is x equal to 0, right? So this is, looks like the TEM 10, these two modes. Right, so the x coordinate index for that m is 1, so you get an x here, remember, and so that you have 0 along x equal to 0. So these two you can check from last class notes also. So these two exactly look like TEM 10. And then correspondingly these two look like TEM 01. Okay. So the properties that we had for the LP modes in step index hold true here also, like for example the number of zeros in the radial direction will be m minus 1 excluding the origin. So that there we got from the Bessel function, here we get it from the Legouis polynomial, but the same thing. Okay, and the number of zeros in the phi direction will be 2l coming from this cosine alpha sine. Right, so let's look at some higher order mode. So LP21. Right, so L is 2, M is 1. So we now have cosine 2 phi or sine 2 phi. Okay. So again we have an R square, so that means null at the origin. Again we have fourfold degeneracy. Right, and so of course there is a null at the origin. And now in the azimuthal direction, now we have 4 zeros, right? So if we take cosine, then we'll have 4 lobes like this. So 0 along pi by 4, right? And intervals of, sorry, yeah, intervals pi by 4 and then pi by 2 plus pi by 4, etc. Okay, so this will be y polarized cosine 2 phi, x polarized cosine 2 phi. And similarly, we have bipolarized sine 2 phi. But will have loops like this. Okay. So again, so for example, recall these modes here, right? So they have 0 along x equal to 0 and x equal to 0 and y equal to 0, right? So they look like what we had for the TEM11, right? So we had x times y. These look like that. These are basically the TEM11 modes. Okay, so and these look like sort of rotated versions of those. Maybe let's look at one more. So here LP02. Okay, so now we have a function here. You can see some r square minus 1. So there, this will go to 0 at a finite r value, right? So you have 1, 0 along the radial direction because n is 2. Okay, so again, so this will have only two-fold degeneracy because L is 0. So there is no azimuthal dependence, as you can see. So there will be a null ring at r equal to 1 over gamma. Okay, so again, this will be the y polarized mode. And this is the null ring. And then the x polarized mode. Okay, and the phase flips as you pass this null ring. Okay, so here we saw that for some modes there's a direct relation, one-to-one relationship between the LP and the TEM modes. Right? These modes and these modes. These other modes also can be written as a superposition of some degenerate TEM modes. Okay, so in general, right? So recall. So there is a lot of degeneracy in both these modes, right? So if you write that expression for the propagation constant again, right? So here you can see the propagation constant depends on only 2m plus L. So modes which have the same value of 2m plus L are degenerate. Similarly, if you look at, so these are for the LP modes. For the TEM modes, we had an expression in terms of M and N, and they look very similar. So here we just had okay. So instead of 2m plus l, we have n minus 1. We have n plus n plus 1. Okay, so again for TEM modes, the modes with same values of m plus n will be degenerate. Okay, so there's a lot of degeneracy in both these modes, and basically, so you can see also if 2m plus l minus 1, so is equal to m plus n plus 1, right? Then these two values of the beta are the same, right? So those correspond to the same degenerate modes, which means, right? So if you take any, so if you take any LPLM mode, for example, okay, you can write it as a superposition of some TEM MN modes. Okay, where the M and N are such that, so this is for all M and N such that M plus N plus 1 is equal to 2L plus M minus 1. Okay, so given some LP mode with some indices L and M, you find out what 2L plus M minus 1 is, that's some number, right? And then you find what M and N values could be corresponding to that number. Those modes will add up with some weights to give you this LP. Okay. So in some cases, you can see that some of these are 0 and only one TEM mode contributes, like for example, LP01, this is just 0, 0, right? So for 0, 1, this is 0 plus 1 minus 1, so sorry, this is 2m plus l, right? Yeah, 2m plus l. So for 0, 1, this is 1, right? So that means m plus n plus 1 should be 1. So the only way that can be is m and n both are 0, right? So LP01 is just TM00, which we saw, right? Similarly, so if you have LP11, so that means here it will be 2 plus 1 minus 1, right? So that this is now 2, right? So that means you can see here n plus n has to be equal to 1. So either m is 1, n is 0, or m is 0, m is 1, right? So TEM01 or 10, right? That's how you get the different LP11 modes. Right? And similarly for, so for example, for 2, 1, LP21, this will be 2 times 1, m is 1, so 2 plus 2 minus 1, so the 3. So m plus n plus 1 should be equal to 3, which means m plus n should be equal to 2. So the combinations possible are 2, 0, 0, 2 and 1, 1, right? So you can see these modes are directly coming from this 1, 1. To get these other modes, you will have to probably include 2, 0 and 0, 2. Okay? So, yeah, and similarly the other way around also, right? Given any TEM MN mode, you can write it as a superposition of some LP LM modes, again such that this, you will take the L and M values which satisfy this condition. Okay, so again I need to write it explicitly. Right, so for example, if I take LP21, so this implies what 2m plus l minus 1 is equal to 3. This implies m plus n should be equal to 2. Right, so this I can write as some linear combination of TEM02, TEM20 and TEM1. Okay. So you can see that two of these modes you can directly see is just coming from TEM11. The coefficients for these two are 0. But for these, you need to. Okay, so similarly LP02. So again for LP02, 2m plus L minus 1 is 3 again, which means m plus n is again 2. So this will be the same combination, but now of course with different weights, right? Right, so the same three modes add up in a different way to give you the LP0. So you can try to do this, right? So see what combinations, what are the coefficients I need to come here to get this mode or to get this mode. Okay. Of course, and each mode has some degeneration, so the different degenerate modes will have different combinations. Okay, so yeah, so we'll stop here. Any questions? Any questions in general in all the material covered so far since the beginning? LP11 mode, can you explain? So what is not here? Right, so the mode profile is like this from the solution, right? So the radial part is some r times Gaussian function, right? So you can see the radial part will be 0 at the center and then have some maxima and then decay away, right? So, and then we have an azimuthal dependence, so L is 1, so cosine phi or sine phi, right? So if we take cosine phi, then maximum is at phi equal to 0 and 180, and then we have zeros at pi by 2 and 3 pi by 2. Right? So that's why we have these lobes. If you take sine phi, the lobes rotate by pi by 2. Right, so they look exactly like the LP11 modes in the step index fiber also. Right, in the step index fiber, instead of this here, you had something like J1 or something, right, gamma or something like that. So qualitative, they look the same. J1 also has the same properties like 0 at 0 and right.
Excuse me, sir.
Yeah.
So whenever we talk about TEM modes, is it under the approximation of weakly guiding approximation?
Yeah, so in a waveguide, whenever you talk about, so for example, here we are talking about TEM modes in a fiber, that of course is happening only under the weakly guiding approximation, right? Even that is sort of an approximation, right? Because even from these solutions, we can compute a longitudinal component which is non-zero, but we just say that's very small compared to the transverse component, right? And we sort of discussed in a couple of classes how you cannot have purely TEM modes, right? For solutions in a waveguide, either Ez or Sz has to be non-zero. So yes, this is another approximation. In free space, of course, you can have purely TEM. And as I said, this TEM nomenclature sort of is coming from the fact that in a free space laser cavity, you have these same modes. Okay. So there, they were called TEM modes, and sort of since these have the same profile, they are also called TEM. And of course, in our approximation of solving it in a scalar wave equation with taking this the transverse component of the field, we are also basically approximating it as TEM modes. Right, so even LP modes here are approximately TEM modes. That's how we are solving it. Right? And then we are sort of justifying it by saying that, okay, when we compute the longitudinal component, if we evaluate the magnitude, that comes out to be much smaller, or that magnitude, the ratio of the longitudinal to the transverse component is proportional to this delta. So if delta is very small, that quantity is small and our approximation is valid.
So even in the case of step index profile, the LP modes are superposition of TEM modes only.
So recall in the step index fiber, we couldn't actually solve for TEM modes, right? So in this case, specifically for the square law profile, right, we were able to write it in Cartesian coordinates and then solve using this separation of variables, so we were able to get these TEM, right? But recall in the step index fiber, actually we couldn't do that, right? So actually we just solved for the LP modes in the screen detector, right? Because there we have to also worry about boundary conditions, right? So recall here we are just assuming this profile to extend till infinity, we don't care about boundary conditions. So in the step index case, actually we didn't solve for any TEM modes, right? We couldn't because we couldn't solve that equation in Cartesian coordinates. But we did show that, for example, the LP modes can be seen as a superposition of these vector modes, the HE and EH modes, right? Which are the two solutions. Right, so these HE and EH modes are the two solutions which don't require the scalar wave approximation or the weakly guiding approximation. And then we saw under the weakly guiding approximation, some of these HE, EH modes become degenerate, and then you can write a superposition of them which becomes LP modes. So again, so the point here is like anytime you have a system where you have two sets of solutions, right, which are equally valid, then you should be able to write, of course, one set of solutions as a superposition of the other set of solutions. That's the only way. They're both valid, right?